Let's tackle the questions one at a time. Feel free to specify where you'd like to begin or continue. Chapter 1, Wastewater Characteristics. 1A. State the relationship between ultimate BOD, BODU, COD, and theoretical oxygen demand, TOD. Relationship. Ultimate BOD, BODU. Measures the total amount of oxygen consumed by microorganisms to degrade organic matter in wastewater. COD, chemical oxygen demand, indicates the total quantity of oxygen required to oxidize both biodegradable and non-biodegradable organic matter. TOD, theoretical oxygen demand, represents the calculated oxygen demand based on the stoichiometric oxidation of a chemical compound. The relationship is typically BODU like COD like KOD. 1. What is the typical range of CO-BOD ratios for biological treatment? Answer: the typical CO-B ratio ranges from start 1.5 to 3.0. Lower ratios 1.5 suggest the wastewater is highly biodegradable. Higher ratios 3.0 indicate the presence of non-biodegradable organic compounds. Would you like to move to the next chapter? Chapter 2, Biological Treatment Processes. Compare coagulation and flocculation in terms of process and purpose. Aspect coagulation flocculicles into larger flocks. And process destabilizes colloidal particles using chemicals, promotes aggregation of destabilized particles into larger flocks. Process: rapid mixing to evenly distribute coagulants, gentle mixing to enhance flock formation. Agents used: alum, ferric chloride, or polymers, natural or synthetic polymers, or physical stirring. Time frame: happens quickly, seconds to minutes, takes longer. 2B. Differentiate between nitrogenous BOD and carbonaceous BOD. Aspect: carbonaceous BO, SIBO, NBO, ceramic ammonia. Definition: oxygen demand for degradation of organic carbon compounds. Oxygen demand for the oxidation of nitrogenous compounds, e.g. ammonia. Microorganisms: heterotrophic bacteria, nitrifying bacteria. Dominates in the initial 5-day BOD test, appears after 5 days as carbon sources are depleted. Significance: indicates biodegradable organic pollution, indicates the presence of nitrogen pollution. Would you like to move to the schematic diagram of the sewage treatment plant, Q3? How to tie 3. Draw a schematic diagram of a sewage treatment plant, including removal efficiencies for major treatment stages. Schematic diagram description. The sewage treatment plant typically includes the following stages. 1. Preliminary treatment. Purpose: removal of large solids, grit, and debris. Removal efficiency: 5% of total solids. Processes: screening, grit removal. 2. Primary treatment. Purpose: settles suspended solids and reduces BOD. Removal efficiency: 30 to 35% BOD and 50 to 60% suspended solids. Processes: primary sedimentation tanks. 3. Secondary treatment. Purpose: biological treatment to remove dissolved organic matter. Removal efficiency: 85 to 95% BOD and suspended solids. Processes: activated sludge process or trickling filters. 4. Tertiary treatment. Optional. Purpose: advanced treatment for nutrient removal, disinfection, or polishing. Removal efficiency: 99% of contaminants depending on the process. Let me provide a detailed explanation of the diagram. Stages in the sewage treatment plant. 1. Preliminary treatment. Processes. Screening and grit removal. Purpose. Removes large solids, floating debris, and sand grit that could damage equipment. Efficiency. Removes 5% of total suspended solids. 2. Primary treatment. Processes. Settling tanks where heavier solids settle to the bottom as sludge. Purpose. Reduces suspended solids and organic matter. Efficiency. Removes 30 to 35% BOD and 50 to 60% suspended solids. 3. Secondary treatment. Processes. Biological treatment such as the activated sludge process or trickling filters. Purpose. Decomposes dissolved organic matter using microorganisms. Efficiency. Removes 85 to 95% of BOA and suspended solids. 4. Tertiary treatment, optional. Processes, filtration, sand or membrane, chemical treatment, and UV disinfection. Purpose. Further purifies water for safe discharge or reuse. Efficiency. Can remove up to 99% of contaminants, including nutrients like nitrogen and phosphorus. 5. Sludge treatment. Processes. Anaerobic digestion, dewatering, and sludge drying. Purpose. Stabilizes and reduces the volume of sludge, producing biogas as a byproduct. Use of the diagram. This schematic helps visualize the flow of wastewater through various treatment stages, highlighting the removal of solids and pollutants at each phase. If you have any questions or need additional details, feel free to ask. None of this, tar 4. Explain why chemicals in higher valency states are preferred for the coagulation process. Answer. 1. Higher charge density. Chemicals with higher valency, e.g. Al-Pwthmyphipi, have a greater charge density compared to lower valency ions, e.g. Fe-Pi. This increases their ability to neutralize the negative charges on suspended particles in water. 2. Efficient flock formation. High valency ions form stronger and denser flocks, which settle more quickly and efficiently during sedimentation. Example, aluminum sulfate Al2SO3 and ferric chloride FeCl3 are commonly used. 3. Reduced chemical dosage. Coagulants in higher valency states require lower doses to achieve effective charge neutralization and flocculation. 4. Broad pH range. High valency coagulants are effective over a broader pH range, improving their utility in diverse water conditions. 5. Hydrolysis and precipitation. During hydrolysis, higher valency coagulants form metal hydroxides, e.g. AlOH3, which act as sweep flocks to capture and remove contaminants. Would you like to explore any calculations or examples related to this concept? Task 5. Calculate the theoretical oxygen demand TOD of 300 milligrams of sucrose, C12H22O11. Solution. To calculate THOD, we use the stoichiometric equation for the complete oxidation of sucrose, C12H22O11 plus 12OCO2, right arrow 12CO2 plus 11H2O. Step 1. Molar mass of sucrose. Molar mass of C12H22O11 equals 12 times 12 plus 22 times 1 plus 11 times 16 equals 144 plus 22 plus 176 equals 342. And step 2. Oxygen required for oxidation. From the equation, 1 mole of sucrose requires 12 moles of O2. Molar mass of O2 equals 32 tex g per mole. Oxygen required for 1 mole of sucrose, 12 times 32 equals 384 g of O2. Step 3, BOD calculation for 300 milligrams of sucrose, 300 text milligrams of sucrose, 0.3 text g. Oxygen demand is proportional. Text T equals frac 342, right, times 0.3 equals 0.336. G of OD equals 336, NEMDAS per layer of O2. Sharp final answer. The theoretical oxygen demand for 300 milligrams of sucrose is 336 milligrams per liter. Would you like to explore more on this, or proceed to the next question? Starter 6. The 5-day BOD of wastewater is 220 milligrams per liter. It's calculated at 20 degrees Celsius, given the rate constant K equals 0.1, text days square minus 1. Comment on the nature of the waste based on your findings and illustrate it with a graph. Schar's solution. The relationship between BODU and the rate constant K is given by the first-order reaction equation. BOT equals 1 minus os E grinding T right, where minus BT equals 5-day body 220 energy per liter, K equals 0.11, text T equals 5 text days. Equals step 1, rearrange for ultimate BODU. BODU equals 2, BODU equals frac 1 minus E equal to minus K. Step 2, calculate Nashi T equal to minus KT equals E equal to 20.1 times 5 equals E equal to 0.5, approx 0.65. Step 3, calculate BODU. BODU, 1 minus 220.6065 equals frac 220, 0.39 Fox, 559.1. Text final answer. The ultimate BODU is 559.1 milligrams per liter. Comment on the wastewater characteristics. A high ultimate BOD value indicates strong organic pollution in the wastewater. This suggests the wastewater is heavily contaminated and requires robust treatment before discharge to prevent oxygen depletion in receiving water bodies. Illustration. The BOD curve shows the relationship between oxygen demand and time. 1. BOD SWERN is reached at 5 days. 2. BODU is the asymptote where the curve levels off as oxygen demand approaches completion. Let me know if you'd like me to create a graph to visualize this. Here is the BOD curve. The blue curve represents the oxygen demand over time. The red dashed line marks the ultimate BODU of 559.1 milligrams per liters. The green dashed line indicates the 5-day BOD-DD5 at 220 milligrams per liters. The orange point highlights the value of BOD after 5 days. This graph illustrates how BOD increases over time and asymptotically approaches the ultimate. Let me know if you need further clarification or any modifications. For 7, 10 milligrams of ferrous sulfate, FeSO4, is consumed with lime in a coagulation basin. Determine the quantity of ferrous sulfate and quicklime required to treat 15 mLD, million liters per day, of water. Solution. Step 1. Convert the dose to a mass basis for 1 megaquarters of water. The dose of ferrous sulfate is 10 grams per liter. For 1 text mbecru of water, 1,000 mL, text mass of FeSO score equals 10, text mg 1000 eld equals 10,000, mg equals 10, g per megascroll. Step 2. Calculate the mass for 15 mLD of water. The total water volume is 15 mLD equals 15,000 per day. Total FeSO per day equals 10 times 15,000, 100 grams per day equals 150 per day equals 150 kgrams per day. Step 3. Calculate the amount of quicklime CaO required. The reaction between FeSO4 and CaOH2 is text FeSO4 plus text CaOH2, right arrow text FeOH2 plus text CSO4. From stoichiometry, 1 mole of FeSO4 reacts with 1 mole H2. Molar mass of FeSO4 equals 56 plus 32 plus 4 times 16 equals 152, text G per mole. Molar mass of CaO equals 40 plus 16 equals 56, text G per mole. The mass ratio is mass ratio CaO FeSO4 frac 56, 152, approx 0.368. For every 1 text gram of FeSO4, 0.368 of CaO is needed. Step 4. Total quicklime required. CaO day equals 150 kilograms per day times 0.368 approx 55.2. Final answer. Ferrous sulfate required, 150. Quicklime required, 55.2 text per day. Let me know if you need further assistance or clarification. Angipostate. A coagulation treatment plant with a flow of 2 ml per hour is dosing alum at 30 milligrams per liters. The influent suspended solids concentration is 40 milligrams per liters, and the effluent concentration is 15 milligrams per liter. The sludge produced contains 5% solids with a specific gravity of 2.09. Calculate the volume of sludge disposed of each day. Solution. Step 1. Determine the total flow per day. The flow rate is 2 ml per hour. Daily flow equals 2 texts per hour times 24, text hours day equals 48 texts per day. Step 2. Calculate the suspended solids removed. The removal of suspended solids is delta influent SS, text effluent SS equals 40 memgrams per minus 15 memgrams equals 25. Convert to text G of 5 equals 25. Text G times 1 to 1,000. Mg equals 0.025. G for L equals 25, D25. The total suspended solids removed per day. Text SS removed equals 48 nemsleaf per day times 25 times 1200 equals 1200 to D day equals 1.22. Nash step 3. Determine the volume of sludge generated. The sludge contains 5% solids. Solids fraction equals 5/100, 0.05. The volume of sludge produced, sludge volume SS removed, solids fraction, times text specific gravity. Sludge volume, frac 1.2 text kilograms per day, 0.5 times 2.09, approx 11.5 Ls per day. Final answer, volume of sludge to be disposed of per day, 11.5 Ls per day. Let me know if you need further assistance. Summa 1. What are the important factors considered in the BO test? Solution. The biochemical oxygen demand test is influenced by several critical factors, which include 1. Temperature. The standard test is conducted at 20 circ text C. Higher temperatures increase microbial activity, whereas lower temperatures slow it down. 2. Time duration. The typical test duration is 5 days, BO3. Extended periods can measure the ultimate B-text beyond U. 3. Dilution water. The water used must be free of contaminants but seeded with the appropriate microorganisms. For initial and final dissolved oxygen, DO, the difference between the initial and final DO is used to calculate BD. 5. Microbial population. The presence of viable microorganisms is essential for breaking down organic matter. 6. pH of the sample. The pH must be within the range of CO6.5 to 7.5 C for optimal microbial activity. 7. Toxic substances. The presence of toxic substances, e.g. heavy metals, can inhibit microbial activity, leading to lower BIOD readings. 8. Nutrient availability. Nutrients like nitrogen and phosphorus are essential for microbial growth during the test. Final answer. Key factors considered in the BIOD test include temperature, time duration, quality of dilution water, initial and final DO, microbial population, pH, toxic substances, and nutrient availability. Would you like to move on to the next question? Nash 2. Draw a schematic diagram of carbonaceous B bod and nitrogenous bod NBD and explain the phases on the graph itself. Explanation. In the bod test, there are two primary components. 1. Carbonaceous body, C bod, refers to the oxygen demand exerted by the organic carbon content of wastewater. During the test, microorganisms consume carbon compounds, organic matter, resulting in the depletion of DO. 2. Nitrogenous bod, NB, refers to the oxygen demand exerted by the nitrogen compounds in the wastewater, primarily ammonium, NH-quark-base, and nitrites, NO2-Ms. It involves the nitrification process, where ammonia is oxidized to nitrate by nitrifying bacteria, consuming more oxygen. The graph of BOD over time typically shows two phases. 1. Lag phase, initial stage. Microorganisms are adapting to the environment. During this phase, little or no oxygen consumption occurs. 2. Log phase, exponential phase. During this phase, there is rapid consumption of organic matter, CB body, and an increase in oxygen demand. 3. Stationary phase. Microbial growth slows down, and the available organic matter is nearly consumed. 4. Decline phase. In this phase, nitrogen compounds, NB, are being oxidized nitrification, further depleting the DO levels. Schematic graph. The graph will have time on the x-axis and dissolved oxygen, DO, on the y-axis. The C-BOD curve starts high and decreases quickly as carbon is consumed. The N-BOD curve starts lower than C-BOD and rises after the lag phase as nitrogenous compounds are consumed. Both curves will typically intersect, and N-BOD may continue slightly beyond C-BOD as nitrification completes its process.
Wait.
Would you like me to assist with drawing the diagram or any further clarification? Here is the schematic diagram showing the relationship between carbonaceous body, C-body, and nitrogenous bod, N-body, over time. C-body, blue line, starts high, decreases rapidly as the organic carbon is consumed. N-bod, green line, starts after the lag phase, increases gradually due to the oxidation of nitrogenous compounds, like ammonium, by nitrifying bacteria. The graph illustrates how the oxygen demand changes over time due to the different phases of organic and nitrogenous compound degradation. Let me know if you'd like any further clarification. 3. List and describe water quality parameters: physical, chemical, and biological. Physical parameters. 1. Temperature. Measures the warmth or coldness of water. Affects solubility of gases like oxygen and the rate of biochemical processes. 2. Turbidity. Refers to the cloudiness or haziness of water caused by suspended particles. High turbidity can block sunlight, affecting aquatic life. 3. Color. The appearance of water due to dissolved or suspended substances. Color can indicate the presence of organic compounds, algae, or pollutants. 4. Total suspended solids, TSS, measures the concentration of particles suspended in water, affects aquatic life and water quality treatment processes. 5. Odor, the smell of water which can indicate the presence of pollutants or decomposing organic matter. Chemical parameters. 1. pH, indicates the acidity or alkalinity of water, affects the solubility of nutrients and metals, and is crucial for the survival of aquatic organisms. 2. Dissolved oxygen, DO, refers to the amount of oxygen dissolved in water. Essential for the survival of aquatic life. Low levels can indicate pollution or decomposition. 3. Biochemical oxygen demand, BOD, the amount of oxygen consumed by microorganisms to decompose organic matter. High BOD indicates high levels of organic pollution. 4. Chemical oxygen demand, COD, measures the total oxygen required to chemically oxidize organic matter. A higher COD value suggests higher levels of pollutants. 5. Nutrients, nitrates, phosphates, nitrates, NO3 mares, and phosphates, PO-quercremamaneres, can contribute to eutrophication in water bodies. High levels can promote algae growth, leading to oxygen depletion. 6. Hardness, caused by dissolved calcium and magnesium salts. Affects the taste and suitability of water for industrial or domestic use. Biological parameters. 1. Coliform bacteria, indicator organisms for the presence of pathogenic bacteria. The presence of coliforms suggests contamination of water by fecal matter. 2. Algal growth. The growth of algae in water, influenced by the availability of nutrients, mainly nitrogen and phosphorus. Algal blooms can lead to oxygen depletion and toxin production. 3. Fecal coliforms, a subgroup of coliform bacteria associated with fecal contamination. Its presence indicates potential for waterborne diseases. 4. Phytoplankton and zooplankton. Phytoplankton, plant-like organisms, and zooplankton, animal-like organisms, are essential components of aquatic ecosystems. Their presence and abundance can reflect the overall health of the aquatic system. 5. Biomass of aquatic organisms includes the population of fish, invertebrates, and other organisms. Indicates the ecological health of water bodies. This classification helps to assess the overall health of water bodies and understand the impacts of pollution, guiding the treatment process and environmental protection efforts. Let me know if you'd like further elaboration on any of these parameters. Hadar 4. Explain the phases of bacterial growth. Bacterial growth can be divided into 4 distinct phases, each reflecting the population dynamics and metabolic activity of the bacteria. 1. Lag phase. Description. In this initial phase, bacteria adapt to their environment, but no significant cell division occurs. The bacteria are metabolically active as they synthesize enzymes and other molecules necessary for growth. They adjust to new conditions, such as nutrient availability, temperature, or pH, but aren't yet multiplying. Duration can last from a few minutes to several hours, depending on the conditions. 2. Log phase, exponential growth phase. Description. Bacteria begin to divide at a constant rate, leading to an exponential increase in population. The rate of cell division is at its maximum, and nutrients are consumed rapidly. This phase is characterized by rapid growth, and bacterial cells are most sensitive to antibiotics during this stage. Duration. It continues until essential nutrients start depleting or waste products accumulate. 3. Stationary phase. Description. The growth rate slows down and stabilizes as the number of new cells produced equals the number of cells dying. Nutrients become limited and waste products start to build up. The overall population remains constant, but bacteria may continue to survive by shifting to survival mechanisms like spore formation. This phase can last for a considerable amount of time, depending on available nutrients and the environment. 4. Death phase. Decline phase. Description. As nutrients are exhausted and toxic waste products accumulate, bacteria begin to die off at a faster rate than new cells can be produced. The population decreases exponentially. If environmental conditions remain unfavorable, the bacteria may eventually die out completely. Duration. This phase may continue until the bacteria exhaust all resources or the environment becomes more favorable. These phases are crucial for understanding bacterial behavior in wastewater treatment and other biological processes, such as BOD testing. They help explain why microorganisms behave differently at different stages of growth, affecting their ability to degrade organic matter or contribute to disease transmission. Let me know if you'd like to dive deeper into any phase. Nota 5. Define the terms. Chemoautotrophs and heterotrophs. 1. Chemoautotrophs. Definition. Chemoautotrophs are organisms that obtain energy by oxidizing inorganic compounds, such as hydrogen sulfide, H2S, ammonia, NH3, or iron, Fe+, and use this energy to fix carbon dioxide, CO2, into organic molecules. Characteristics. They do not rely on sunlight for energy. Common examples include certain bacteria found in extreme environments, like hydrothermal vents or sulfur springs, where light is not available but chemical energy from inorganic substances is abundant. Example: Nitrosomonas, which oxidizes ammonia to nitrite, and Thiobacillus, which oxidizes sulfur compounds. 2. Heterotrophs. Definition. Heterotrophs are organisms that obtain carbon and energy by consuming organic material from other organisms. They cannot synthesize their own food and rely on external sources of organic compounds. Characteristics. Heterotrophs include animals, fungi, and many bacteria. They are crucial in ecosystems as decomposers or consumers. They may obtain energy through respiration, either aerobic or anaerobic, depending on the organism. Example: humans, animals, and most bacteria, e.g. Escherichia coli, Streptococcus. Key differences. Energy source. Chemoautotrophs obtain energy from chemical reactions involving inorganic compounds. Heterotrophs obtain energy by consuming organic compounds. Carbon source. Chemoautotrophs fix carbon from CO2. Heterotrophs obtain carbon from organic matter they consume. These terms are important in microbiology and environmental sciences because they help classify organisms based on their energy and carbon sources, which has implications for nutrient cycling and energy flow in ecosystems. Let me know if you'd like further clarification or examples. Tash 6. A. What is the importance of dissolved oxygen DO in water? How does it assist in wastewater treatment? How is the DO level maintained in streams, and what factors affect it? 1. Importance of dissolved oxygen DO in water. Essential for aquatic life. Dissolved oxygen is crucial for the respiration of aquatic organisms, including fish, invertebrates, and microorganisms. The concentration of DO determines the health of aquatic ecosystems. Low levels of DO can stress or even kill aquatic life. Wastewater treatment. In wastewater treatment processes, particularly in aerobic biological treatment methods, like activated sludge, microorganisms require oxygen to degrade organic pollutants efficiently. The DO level in the system must be maintained to support microbial activity and ensure the efficient breakdown of organic matter in the water. 2. Role of DO in wastewater treatment. TACST, aerobic biobiological treatment. Microorganisms break down organic pollutants by using oxygen in aerobic conditions, converting organic matter into simpler substances such as carbon dioxide, water, and new biomass. A sufficient DO level is essential for maintaining the metabolic processes of aerobic microorganisms, ensuring optimal treatment of wastewater. DO in the aeration tank. In activated sludge and other aeration-based treatment systems, aerators or diffusers are used to introduce oxygen into the system, which facilitates the growth of aerobic microorganisms that degrade organic pollutants. 3. Maintenance of DO levels in streams. Natural DO regeneration. Streams and rivers maintain DO levels through natural processes like photosynthesis by aquatic plants and algae, which produce oxygen during daylight hours. Turbulent water flow also increases the oxygen exchange between air and water. Factors affecting DO in streams. Temperature. Warmer water holds less oxygen, leading to lower DO levels in warmer streams. Flow rate. Fast-moving water can absorb more oxygen from the air, while slow-moving water may have lower DO concentrations. Pollution. Organic pollutants can consume DO as they decompose, leading to oxygen depletion. Higher pollution loads, e.g. leak air, from wastewater discharge can lower DO levels. Algal bloom. High concentrations of algae can lead to excess oxygen production during the day, but oxygen depletion can occur at night when algae consume oxygen. 4. Factors affecting DO levels in water. Biological activity. Microbial respiration, plant growth, and decomposition of organic material all consume oxygen in the water. Temperature. Higher temperatures decrease the solubility of oxygen in water, reducing DO levels. Water movement. Faster moving water, like in rivers or streams, tends to have higher DO concentrations due to increased gas exchange. Pollution. High organic load from sewage or agricultural runoff increases oxygen demand, reducing available DO in the water. Atmospheric pressure. Lower atmospheric pressure at higher altitudes results in lower DO saturation in water. Maintaining adequate DO levels is crucial for both healthy aquatic ecosystems and effective wastewater treatment. Insufficient DO can lead to the failure of biological treatment processes and harm aquatic life. Let me know if you'd like further details or examples. Pattern 6. In a standard BOD test with a 130 dilution and seeded water, saturation DO equals 9.2 milligrams per L. After 5 days, DO waste equals 2 milligrams per DO seed 8 milligrams. Calculate the 5-day BOD SAR. We use the formula for calculating B from the dissolved oxygen DO measurements. Text BOD SAR B equals OF times text dilution fact times text volume of sample plus text volume of dilution water. Star 6. In a standard BOD test with a 130 dilution and seeded water, saturation D equals 9.2 milligrams per hour. After 5 days, DO waste equals 2 milligrams per liter. DO seed equals 8 milligrams per liter. I. Calculate the 5-day BOD. We use the formula for calculating BOD from the dissolved oxygen DO measurements. Tracks DOIs DOF times text dilution factor times volume of sample plus text volume of dilution water. Or 6C. Calculate the theoretical oxygen demand, TOD, for C3H*NO2. To calculate the theoretical oxygen demand, TOD, for a compound, we need to know the molecular formula and the stoichiometry of the reaction that occurs when the compound is oxidized. Molecular formula, C3H*NO2, which is a common organic compound such as alanine or similar amino acids. Reaction? In a general case, the oxidation of an organic compound such as C3H*NO2 to CO2 and H2O can be represented by the following reaction. Text C3HNO2 plus O2, right arrow 3CO2 plus 4H2O. To calculate the theoretical oxygen demand, we must balance this reaction and then determine how much oxygen is required to oxidize the given compound completely. Step 1. Determine the number of oxygen molecules required to completely oxidize one molecule of C3H*NO2. The balanced equation shows that for every 1 mole of C3H*NO2, 3 moles of CO2 and 4 moles of H2O are produced. Now, the stoichiometry of the oxygen required for this reaction is as follows. For each CO2 molecule, 1 mole of O2 is required. For each H2O molecule, 0.5 moles of O2 are required. So, the total oxygen required for complete oxidation of C3H*NO2 is text O2 required equals 3 moles of O2 per CO2 plus 4 times 0.5 moles of O2 per H2O. 3 plus 2 equals 5, text moles of O2. Step 2, molecular weight of C3H*NO2. The molecular weight M of C3H*NO2 is calculated as M equals 3 times 12 plus 7 times 1 plus 1 times 14 plus 2 times 16. M equals 36 plus 7 plus 14 plus 32 equals 89. Text step 3. Calculate the theoretical oxygen demand, TOD. For 1 mole of C3H*NO2, the oxygen required is 5 moles of O2, and the molecular weight of oxygen, O2, is 32 grams per mole. Thus, the THOD per mole of C3H*NO2 is text OD equals 5 times 32 equal 160, G of O2 per mole of C2NO2. To find THOD per gram of C3H*NO2, divide by the molecular weight of C3H*NO2. Text TOD per gram equals frac 160, text GO2. 89, G per mole equals 1.80, text GO2 per gram of C3H gram. So the theoretical oxygen demand for C3H*NO2 is approximately 1.80 grams O2 per gram of C3HNO2. Let me know if you'd like to proceed with the next question or further explanations. Task 6. D. Between BOD and COD, which one usually has a higher value? Justify your answer and describe the safe disposal limits of BOD. BOD, biochemical oxygen demand, and COD, chemical oxygen demand, are two different measures of the oxygen demand exerted by organic materials in water. 1. Which one is usually higher, BOD or COD? COD, chemical oxygen demand, usually has a higher value than BOD, biochemical oxygen demand. Reason? COD measures the total oxygen demand required to oxidize all organic and inorganic materials in water, including both biodegradable and non-biodegradable substances, through chemical means, usually using a strong oxidizing agent such as potassium dichromate. On the other hand, measures only the oxygen consumed by biodegradable, organically oxidizable materials in the water, typically in the presence of microorganisms. Since COD includes the oxygen demand for both biodegradable and non-biodegradable substances, its value is typically higher than BOD, which only accounts for biodegradable substances. 2. Justification for higher COD. COD encompasses both biodegradable and non-biodegradable organic substances, as well as certain inorganic compounds. Thus, it will always be higher than BOD for most natural and industrial wastewater. BOD, however, only reflects the oxygen demand for substances that can be biologically degraded, which is generally a smaller fraction of the total organic material in wastewater. 3. Safe disposal limits of BOD. B-BOD is used to assess the potential environmental impact of wastewater on aquatic ecosystems. If wastewater with high BOD is discharged into a water body, it can deplete dissolved oxygen, DO, in the receiving water, affecting aquatic life. The safe disposal limit for BOT depends on the receiving water body and local regulations, but typical limits are as follows. For municipal sewage, BOD should ideally be below 30 milligrams per star after secondary treatment, in compliance with common regulatory standards. For industrial effluents, BO limits can vary, but values are generally around 50 milligrams per liters to 100 milligrams per liters, depending on the type of industry and the local environmental standards. In some cases, stricter limits may be applied to sensitive environments, such as rivers or lakes used for drinking water supply. Let me know if you would like to proceed with further questions. TAPTA 7. A. Classify aerobic and anaerobic processes with examples. Aerobic processes. Definition. Aerobic processes are biological processes that occur in the presence of oxygen, where microorganisms such as bacteria break down organic matter by using oxygen. Examples. 1. Activated sludge process. This is the most common method used in municipal wastewater treatment. It involves aerating wastewater in a large tank where bacteria break down organic materials. 2. Trickling filter. In this process, wastewater is passed over a bed of microorganisms that degrade the organic matter, utilizing oxygen in the process. 3. Oxidation ponds, shallow man-made ponds where wastewater is exposed to oxygen via natural aeration and biological activity. Anaerobic processes. Definition. Anaerobic processes occur in the absence of oxygen, where microorganisms degrade organic matter without using oxygen. These processes typically produce methane, CH4, as a byproduct. Examples. 1. Anaerobic digestion. Used in wastewater treatment to treat sludge, anaerobic bacteria break down organic solids in a sealed tank, producing biogas, mainly methane, and reducing the volume of the sludge. 2. Septic tanks. In septic systems, organic waste is partially broken down by anaerobic bacteria before being disposed of or further treated. 3. UASB, upflow anaerobic sludge blanket. A type of anaerobic treatment used for high-strength wastewater. It utilizes the anaerobic bacteria to break down organic material. 7. B. Define the hardness of water and explain its problems if not removed. Describe the lime soda process for softening water. Hardness of water. Definition. Hardness in water refers to the concentration of dissolved minerals, primarily calcium, Ca squaribahystast, and magnesium, Mg ions. These ions react with soap to form insoluble precipitates and are responsible for the hardness of water. Problems caused by hard water. 1. Scaling. Hard water causes scale formation in pipes, boilers, and water heating systems. This reduces the efficiency of equipment and increases maintenance costs. 2. Increased soap consumption. Hard water requires more soap or detergent to produce a lather, leading to increased costs and environmental impact. 3. Clogging. Hard water can cause clogging of pipes and water-using appliances, reducing the lifespan of these systems. 4. Reduced detergent efficiency. Hard water interferes with the cleaning power of detergents, which can lead to poor washing results. Lime soda process for softening water. Process. The lime soda process is a widely used method for softening hard water. It involves adding lime, CaOH2, and soda ash, Na2, to the water to precipitate calcium and magnesium as insoluble salts, thereby reducing water hardness. Steps. 1. Lime, CaOH2, is added to the water, which reacts with calcium hardness, Ca goodbyes to form calcium carbonate, CaCO3, precipitate. 2. Soda ash, Na2CO3 star, is added to precipitate magnesium hardness, Mg queries as magnesium hydroxide, MgOH2, along with calcium hardness if required. Reaction. For calcium hardness, text C8 squared 2 plus plext CaOH2 right arrow text CaCO3 S plus text H2 text O. For magnesium hardness, text Mg2 plus text Na2 tech 3 right arrow text MgCO3 est 2 Na quest plus outcome. The insoluble precipitates are then removed through filtration, leaving the water softened. Sever C. A water sample contains the following: sodium 46.5 milligrams per liters, calcium 36.8 milligrams per, magnesium 15.6 milligrams per liter, chlorine 88.6 milligrams per liter, SO4 178.8 milligrams per liter, HCO3 204.5 milligrams per liter. Calculate total hardness, permanent hardness, and temporary hardness expressed as CaCO3 using atomic weights. C12. CH 40, Mg 24, O, 16, Na 23, 32, 35.5, solution 1. Temporary hardness due to bicarbonates. Formula text temporary hardness, CaCO3 equivalent from HCO3-. For calcium bicarbonate, text SWERC 22 plus 2 HCO, right arrow 3S plus text H2 text O. Convert Ca quitbi and HCO3 nanos concentrations to CaCO3 equivalents. 2. Permanent hardness due to sulfates and chlorides. Sulfates and chlorides are not removable by boiling, and they contribute to permanent hardness. For calcium sulfate, text Ca2 plus, text SO42, right arrow, text CSO44S. For magnesium sulfate, text Mg2 plus, SO4, text MgSO4. 3. Total hardness. Combine both temporary and permanent hardness for the total hardness value. Use the appropriate conversion factors and apply the given concentrations of calcium, magnesium, and bicarbonate. Let me know if you'd like me to perform the detailed calculations. Let's go ahead and calculate the total hardness, temporary hardness, and permanent hardness expressed as CaCO3 equivalents. Question 1. Temporary hardness due to bicarbonates. Temporary hardness arises due to the presence of calcium bicarbonate, CaHCO32, and magnesium bicarbonate, MgHCO322. These can be removed by boiling, as they form insoluble salts. First, we'll calculate the temporary hardness due to calcium and magnesium. Calcium hardness, for calcium bicarbonate, text Ca2 plus 2 HCO3 right arrow text CaCO3S plus H2 text O. The equivalent weight of calcium bicarbonate, CaHCO32, is 100 grams per mole. Ca equals 40, HCO3 equals 61. The formula to calculate hardness in terms of CaCO3 is text hardness in TaCO3 equals frac text Ca2 plus times 100, 40. Given the Ca Crais concentration is 36.8 milligrams per LR, text temporary hardness equals frac 36.8 times 100 equals 92 text mg per liter as CaCO. Magnesium hardness, for magnesium bicarbonate, text Mg2 plus 2 text HCO3 swarmase, right arrow text Mg3S plus text H2 text O. The equivalent weight of magnesium bicarbonate MgHCO32 is 146 grams per mole. Mg equals 24, HCO3 equals 61. The formula to calculate hardness in terms of CaCO3 is hardness in CaCO3, 3 equal fracs Mg2 plus times 146.24. Given the Mg5 concentration is 15.6 milligrams, text temporary hardness equal frac 15.6 times 146.24 equals 95.4, text mg per liter as CaCO3. Total temporary hardness, text temporary hardness 92 plus 95.4, 187.4, mg per liter as KCO2. 2. Permanent hardness due to sulfates and chlorides, STRATAGs. Permanent hardness arises due to salts like calcium sulfate, CSO4, magnesium sulfate, MgSO4, and other salts like chlorides. Calcium sulfate. The molecular weight of calcium sulfate, CSO4, is 136.2 grams per mole, Ca equals 40, S4 equals 64. The conversion factor to CaCO3 is text hardness in CaCO3 equals frac text Ca2 plus times 136.2, 40. For calcium concentration of 36.8 milligrams per las, text permanent hardness from Ca equals frac 36.8 times 136.2, 40 equals 125.3, and to the earth as CaCO3. The magnesium sulfate. The molecular weight of magnesium sulfate, MgSO, is 124 grams per mole, Mg equals 24, S equals 32, O4 equals 64. The conversion factor to CaCO3 is text hardness in CaCO3 equals Mg2 plus times 120.4, 24. For magnesium concentration of 15.6 milligrams per dex, permanent hardness from Mg frac 15.6 times 120.4, 24 equals 78.1, text mg per liter as CaCO3. Total permanent hardness equals 125.3 plus 78.1 equals 200 per liter as CaCO3. Total hardness. The total hardness is the sum of temporary and permanent hardness. Total hardness equals 187.4 plus 203.8 equals 390.8 as CaCO. Summary. Temporary hardness equals 187.4 milligrams per kilo as CaCO3. Permanent hardness, 203.4 milligram GAR as CaCO3. Total hardness, 390.8 milligram as CaCO3. Let me know if you'd like further clarification or adjustments. 1. Coagulation and flocculation. A. Discuss the processes of coagulation and flocculation. B. Compare hydrophobic and hydrophilic constants. C. Calculation results. 1. Calcium hardness, 92, text membranes earlier as Ca for earlier as CaCO3. 2. Magnesium hardness as Let's continue with the next step. Next question. Classify pollutants based on their solid content. Pollutants in water bodies can be classified based on the nature and size of solids they consist of. The main types of solids in water can be broadly classified as follows. 1. Total solids, TS. Definition. Total solids are the sum of both dissolved and suspended solids in water. Components, dissolved solids, TDS. These are solid particles that are dissolved in water, and they typically include salts, minerals, and organic matter that are not easily filtered out. Examples include sodium chloride, NaCl, calcium carbonate, CaO3, and other dissolved ions. Suspended solids. These are solid particles that are suspended in water but can settle over time. Suspended solids often consist of particles like silt, algae, and organic matter. 2. Fixed solids. Definition. Fixed solids are the solids that remain after the sample is heated to a high temperature, usually 550 degrees Celsius, to remove volatile components. These solids are usually made up of inorganic materials. Examples: sand, silt, and other minerals present in the water. 3. Volatile solids. Definition. Volatile solids are those solids that can be vaporized at high temperatures, typically at 550 degrees Celsius. These solids are mostly organic compounds. Examples: organic matter, including decaying plant material and microorganisms. 4. Settlable solids. Definition. Settlable solids are those that will settle at the bottom of a container due to gravity within a given period, usually 1 hour. Examples: larger particles like sand, gravel, or organic particles that are heavy enough to settle at the bottom. 5. Dissolved organic matter. Definition. These are organic compounds dissolved in water, which are typically not visible, but may contribute to pollution when they decompose, especially in wastewater. Examples: carbohydrates, proteins, and fatty acids. 6. Floating solids. Definition. Floating solids are those that remain at the surface of water and do not sink, often due to low density or surface tension. Examples: oils, plastics, and other hydrophobic materials. Conclusion. Pollutants based on their solid content can be classified into dissolved, suspended, floating, fixed, and volatile solids. These categories help in understanding the water's quality and in the design of treatment processes. Each type of solid requires different methods for removal, such as filtration, sedimentation, or chemical treatment. Let me know if you would like to move forward with the next section. Let's move on to the next question. Why is alkalinity measured? At which pH levels are carbonate, bicarbonate, and hydroxides significantly present? Answer. Alkalinity measurement. Alkalinity is a measure of the water's ability to neutralize acids. It is important because it indicates the buffering capacity of water, which helps resist changes in pH when acids are introduced. Alkalinity is mainly due to the presence of bicarbonates, HCO3 marinase, carbonates, CO3 squarebinase, hydroxides, OH bands, and sometimes phosphates and other ions. Importance of measuring alkalinity. 1. Buffering capacity. Alkalinity helps in maintaining the pH stability of water, which is important for aquatic life and the efficiency of water treatment processes. 2. Water treatment. In processes like coagulation, flocculation, and softening, alkalinity must be controlled to prevent pH fluctuations that could hinder treatment processes. 3. Environmental monitoring. Alkalinity is a key parameter in assessing the health of water bodies, as sudden changes in alkalinity can indicate pollution or harmful runoff. Presence of carbonates, bicarbonates, and hydroxides at different pH levels. The form in which alkalinity compounds exist depends on the pH of the water, as their chemical equilibria change with pH. 1. Hydroxide OH- significant at pH 11 mers. Hydroxide ions are present in basic alkaline water and are responsible for high alkalinity at elevated pH values. 2. Carbonate CO3 squargnamons, significant at pH 9.5 to 11. At higher pH, carbonates are the dominant form of alkalinity. The carbonate-bicarbonate equilibrium plays a crucial role in buffering at these pH levels. 3. Bicarbonate HCO3 monomers, significant at pH 6.5 to 9.5. Bicarbonates are the most important form of alkalinity in natural waters and are abundant in slightly alkaline to neutral waters. 4. Carbonic acid, H2CO3 wasnatawadi, present below pH 6.5. At low pH, carbonic acid, which dissociates into hydrogen ions and bicarbonates, contributes to alkalinity, though its role is limited compared to bicarbonates and carbonates. Alkalinity in water, pH 6.5, carbonic acid and a small amount of bicarbonates are present. pH 6.5 to 9.5, bicarbonates dominate. pH 9.5, carbonates and hydroxides dominate. Conclusion. The measurement of alkalinity is crucial for maintaining the stability of pH in water systems, ensuring proper treatment processes, and protecting aquatic life. The form of alkalinity compounds present, carbonate, bicarbonate, hydroxide, depends on the pH of the water. Let me know if you need further details or want to continue. Let's move on to the next question. Question. Classify pollutants based on their solid content. 2. Answer. Pollutants in wastewater can be classified based on their solid content. The classification helps in understanding the treatment processes required for removing solids from water. The major categories of pollutants based on solid content are 1. Total solids, TS. These are all the solids present in water, including both suspended and dissolved solids. It is classified into total suspended solids, TSS, solids that are not dissolved in water and are removed by filtration or sedimentation. Total dissolved solids, TDS, solids that are dissolved in water and cannot be removed by filtration. 2. Suspended solids, SS, solids that are present in the water in the form of particles and are suspended due to turbulence. These particles can range in size and are typically removed through physical processes such as sedimentation, coagulation, and filtration. Suspended solids can be organic, biodegradable, or inorganic, non-biodegradable, depending on their composition. 3. Settlable solids. These are a subset of suspended solids that can be removed by gravity settling over time. Settlable solids are typically larger in size and more easily removed in primary treatment processes. 4. Colloidal solids. Solids that are too small to settle by gravity, but are larger than molecules that would pass through a filter. Colloidal solids can be difficult to remove and require specialized treatment, such as coagulation and flocculation. 5. Dissolved solids. Solids that are completely dissolved in water and cannot be removed by conventional filtration. These are typically salts, minerals, and other substances that have dissolved into the water. Haberk, pollutant classification based on solid content. 1. Inorganic solids. These include salts, metals, and other minerals. They are usually dissolved, TDS, or present as suspended solids. 2. Organic solids. These include biodegradable materials such as plant material, waste from animals, and other organic compounds. Organic solids can be removed via biological treatment processes like BOD and COD tests. 3. Volatile solids. Organic solids that can be vaporized at high temperatures. These are often used to measure the organic content of sludge in wastewater treatment. Conclusion. Classifying pollutants by solid content is essential in wastewater treatment. It helps determine which treatment processes, like filtration, sedimentation, or biological treatment, should be used for effective removal. High question, why is alkalinity measured? At what pH levels are carbonate, bicarbonate, and hydroxide ions significantly present? Answer. 1. Importance of measuring alkalinity. Alkalinity is a measure of the ability of water to neutralize acids. It primarily reflects the presence of certain dissolved ions, such as bicarbonates, carbonates, and hydroxides, which can react with acids to neutralize them. Alkalinity is important for several reasons. Buffering capacity. It helps maintain a stable pH in water, preventing large fluctuations that could be harmful to aquatic life and various biological processes. Water treatment. In water and wastewater treatment, knowing the alkalinity helps in adjusting the correct amount of chemicals, like acids or bases, to achieve the desired pH level. Corrosion control. In industrial and municipal water systems, alkalinity levels affect the rate of corrosion in pipes and equipment. Proper alkalinity can prevent excessive wear and damage caused by acidic conditions. 2. pH levels and presence of carbonate, bicarbonate, and hydroxide ions. The presence of various alkaline substances in water depends on the pH of the water. The following table summarizes the dominant species at different pH ranges. At pH 10 and above, alkaline conditions, hydroxide ions, OH-MENs, become significantly present. Carbonates, CO3-MENs, are also present, but at higher pH levels, the concentration of hydroxide ions will surpass carbonate ions. At pH 8.3 to 10, slightly alkaline conditions, carbonate ions, CO3-MENs, are dominant. Bicarbonate ions, HCO3-MENs, also contribute, but to a lesser extent. At pH 6.5 to 8.3, neutral to slightly alkaline conditions, bicarbonate ions, HCO3-NANs, are the dominant species. Carbonate ions are still present, but in lower concentrations. At pH 5.6 to 6.5, slightly acidic conditions, bicarbonate ions, HCO3, dominate. The concentration of carbonate ions is significantly reduced, and hydroxide ions are minimal. At pH below 5.6, acidic conditions, bicarbonate ions are almost absent. Carbonate ions and hydroxide ions are almost non-existent. The solution becomes acidic, and hydrogen ions, H-bis, dominate. Summary of pH and species. pH 10+, predominance of OH and CO3 bands. pH 8.3 to 10, CO3 frictionans is dominant, HCO3 is present. pH 6.5 to 8.3, HO3 is dominant with small amounts of CO3 frenesimness. pH 5.6 to 6.5, mainly HCO3. pH 5.6 dominates. Little to no CO3 swears CO3H or OO-gomang. Conclusion, alkalinity is measured to understand the water's buffering capacity, assess its potential for neutralizing acids, and guide water treatment decisions. The significant species present vary depending on the pH, with hydroxide ions dominating in highly alkaline conditions, bicarbonates in neutral to slightly alkaline conditions, and carbonate ions in higher alkaline conditions. Question. Classify pollutants based on their solid content. Answer. Pollutants in wastewater can be classified based on the solid content into the following categories. 1. Total suspended solids, TSS. Definition. These are particles that are suspended in water and cannot pass through a filter. They can include dirt, debris, and organic matter. Sources. Agricultural runoff, industrial discharge, sewage, etc. Impact. High levels of TSS can reduce the quality of water, increase turbidity, affect aquatic life, and reduce the efficiency of water treatment processes. 2. Settleable solids. Definition. These are solid particles that settle out of water due to gravity when the water is allowed to stand undisturbed. Sources. Industrial effluents, wastewater treatment plants, stormwater runoff. Impact. If settleable solids are not removed, they can cause blockages in treatment facilities, contribute to sedimentation in water bodies, and affect water quality. 3. Colloidal solids. Definition. These are extremely fine particles that remain suspended in water and do not settle easily, but can be removed through coagulation or filtration. Sources. Wastewater from industries like paper mills, textile mills, and chemical plants. Impact. Colloidal solids contribute to high turbidity and can negatively affect aquatic ecosystems by blocking light and reducing oxygen levels. 4. Dissolved solids. Definition. These are solids that are completely dissolved in water and cannot be filtered out. They are present in the form of ions or molecules. Sources. Salts, minerals, chemicals used in industries, and fertilizers. Impact. High levels of dissolved solids can lead to water salinity, affecting both aquatic life and the usability of water for domestic and industrial purposes. 5. Organic solids. Definition. These are solid materials that are composed of organic compounds, which can be biodegradable. Sources. Organic waste from households, food industries, agricultural runoff, and sewage. Impact. Organic solids can decompose in water, consuming oxygen and leading to the production of biochemical oxygen demand, BOD. High organic solids content can lead to oxygen depletion in water bodies. 6. Inorganic solids. Definition. These are solid particles that are non-biodegradable and do not originate from organic sources. Sources. Industrial effluents containing heavy metals, construction debris, and mineral waste. Impact. Inorganic solids can persist in the environment for long periods and may be toxic to aquatic life, posing environmental and health risks. Part conclusion. Pollutants based on solid content are categorized into suspended solids, settleable solids, colloidal solids, dissolved solids, organic solids, and inorganic solids. Each category has distinct characteristics, sources, and impacts on water quality, making it crucial to manage these solids during water treatment processes. Question. The pH of a sample is 8. The volume of sulfuric acid consumed during titration is 6 milliliters. Calculate the different forms of alkalinity. 3M. Answer. To calculate the different forms of alkalinity in a water sample, we will need to consider the reactions involved with different alkalinity forms: carbonate alkalinity, bicarbonate alkalinity, and hydroxide alkalinity. The titration with sulfuric acid allows us to measure the overall alkalinity, which can then be split into its components. Step 1. Determine the total alkalinity. Given minus pH equals 8, volume of sulfuric acid consumed equals 6 milliliters, 0.06 L. Normality of sulfuric acid equals 0.1 N, common assumption for titrations with standard acid. The total alkalinity as memogram per liter of CaCO3 is calculated using the formula equals frac text N times 50,000 text volume of sample, where A and N equals normality of acid, 0.1 N, V equals volume of sulfuric acid used, 6 milliliters equal 0.006 EL. 50,000 equals constant for converting to mg's per liter of CaCO3. Volume of sample equals 100 milliliters, common in lab practice. Now, substitute the values. Text total alkalinity equals frac 0.1 times 0.006 times 50,000, 100 equals 30. Text mg per liter as CaCO3. So the total alkalinity in the sample is nary 30 millimilligrams per liters. As step 2, determine forms of alkalinity. Given the pH of 8, the sample contains bicarbonate alkalinity and possibly hydroxide alkalinity. At a pH of 8, carbonate alkalinity is negligible because it is present predominantly as bicarbonate, HCO3 minors. Hydroxide alkalinity is typically present only at higher pH values, 10. So in this case, it can be considered negligible. Thus, the alkalinity in the sample is primarily due to bicarbonates, HCO3. Conclusion: total alkalinity, 30 milligrams per milliliter as CaCO3. Bicarbonate alkalinity, 30 milligrams per milliliter as CaCO3. Hydroxide alkalinity negligible at pH 8. Carbonate alkalinity negligible at pH 8. Therefore, all of the alkalinity is present as bicarbonate. Question. Calculate the 5-day BOD, blodiswar, ultimate BODN, and BOD at 15 days for a wastewater sample. Given initial DO in a BOD bottle, 7.8 milligrams per. Final DO in a BOD bottle, 4.0 millicurie. Dilution factor, 5. BOD bottle volume, 300 milliliter. K rate constant, 0.1 day at 20 degrees Celsius. BODN ultimate bot, 482 milligrams per liter. Temperature adjusted BOD spike calculation for 15 days at 14 degrees Celsius. Answer. Step 1. Calculate the 5-day BOD sparse. To calculate the 5-day BOD, we use the formula. Text BOD 5 equals frax initial DO, text final DO. Given initial DO equals 7.8 milligram per liter, final DO equals 4.0 milligrams per liter. Dilution factor equals 5. Substitute the values. Frac 7.8 minus 4.0, 5, frac 3.8 equals 0.76. So BOD through equals 0.76 milligram. Step 2, calculate the ultimate BOD star. To calculate the ultimate BOD, we use the first order decay formula for BOD. Text BOD T equals text BOD inf D, left 1 minus E minus KT right. Where minus BOD ultimate BOD equals 482 milligrams per meter, K equals 0.1 days, T equals 5 days. Rearrange to solve for BODN at 5 days. Text BOD 5 equals 1 minus E minus T times 5. Substitute the values. Text BOD 5 equals 482. Left 1 minus E 0.1 times 5 equals 482. Left 1 minus E the minus 0.5. We can calculate. Text BOD 5 equals 482. 1 minus 6065 right equals 482 times 0.3935 equals 189.9. So BOD equals 189.9 milligrams per liter, calculated from the ultimate BOD using first order kinetics. Step 3. Calculate the BOD at 15-day deal. To calculate the BOD at 15 days, we use the same formula. Text BOD of 15 equal text BOD inf D, left 1 minus E minus K times 15 right. Substitute the values. 10 minus 15 equals 482, left 1 minus E minus 0.1 times 15 right equals 482. Left 1 minus E to the minus is 1.5. We can calculate both 15 equals 482, left 1 minus 0.2231 right equals 482 times 0.7769 equals 374.4. So next, MBO equals 374.4 milligrams per liter. Conclusion, BOD equals 189.9 milligrams per liter, calculated using first order decay. BODM, ultimate BO 182 milligram of this taro. BO 374.4 milligram of this. The BOD is highest at 15 days and lowest at 5 days, as expected, reflecting the biodegradation over time. The ultimate BOD, BODN, represents the total oxygen demand from the sample over an infinite period. Let's move on to the next question. Question. Discuss the processes of coagulation and flocculation, highlighting their differences. Coagulation. Coagulation is the process of destabilizing the fine suspended particles, colloids, and dissolved impurities in water. This is typically achieved by adding chemicals known as coagulants, e.g. alum ferric chloride, which neutralize the charges on particles, allowing them to aggregate. The particles form microflocks, which are then easier to remove in subsequent treatment stages. Coagulation works best at a slightly acidic pH. Key points. Coagulants. Chemicals like alum, Al2SO3, ferric chloride, FeCl3. Process. Chemicals are added to water and rapid mixing occurs to break down and destabilize colloids. Purpose: to neutral electrical charges on particles, causing them to clump together into larger particles, called flocks. Flocculation. Flocculation is the gentle stirring or mixing process that follows coagulation. It encourages the growth of larger flocks by promoting the collision and aggregation of coagulated particles. The process is slower and requires lower intensity mixing than coagulation to allow larger flocks to form, which are then removed by sedimentation or filtration. Key points. Process: slow mixing after coagulation. Purpose: to promote the aggregation of destabilized particles into larger flocks that can settle out or be filtered. Key differences. 1. Purpose: to destabilize particles and reduce their electrical repulsion. Flocculation: to aggregate destabilized particles into larger flocks. 2. Chemical versus physical. Coagulation, a chemical process involving the addition of coagulants. Flocculation, a physical process involving slow mixing to form larger flocks. 3. Mixing intensity. Coagulation, rapid mixing to ensure uniform distribution of coagulants. Flocculation, gentle mixing to allow particles to collide and aggregate. 4. Time. Coagulation, short duration, quick addition and mixing of coagulants. Flocculation, longer duration to allow flock formation. Let me know if you'd like to move to the next one. Question. Compare hydrophobic and hydrophilic constants. 2. Hydrophobic constant. Definition. The hydrophobic constant refers to the property of a substance that tends to repel water. Hydrophobic substances are nonpolar and do not interact well with water molecules. Nature. Hydrophobic substances, when dissolved in water, will aggregate or cluster together to minimize contact with water. These substances typically have low solubility in water. Examples. Oils, fats, and waxes are common examples of hydrophobic substances. Hydrophobic constant value. A higher hydrophobic constant indicates a stronger tendency to repel water. Hydrophilic constant. Definition. The hydrophilic constant refers to the property of a substance that tends to attract or interact with water molecules. Hydrophilic substances are polar and easily form hydrogen bonds with water. Nature. Hydrophilic substances tend to dissolve in water or form stable colloidal solutions as they interact favorably with water molecules. Examples. Salt, sugars, and alcohols are common examples of hydrophilic substances. Hydrophilic constant value. A higher hydrophilic constant indicates a stronger tendency to interact with and dissolve in water. Key differences. Water interaction. Hydrophobic. Repels water, does not dissolve.